We saw that we can use Laplace transforms to solve initial value problems. Now let's take a look at this process with a generic differential equation, which will have the form dy dt equals some function of t and y. We start by taking the Laplace transform of both sides. On the left, we'll have Laplace transform of the derivative dy dt, and on the right, we'll have the Laplace transform of our generic function f of t and y. On the right, we'll need to use the rules that we discover to find the Laplace transform there. On the left, we found that the Laplace transform of dy dt is s times the Laplace transform of y minus y of 0. We computed this in an earlier video. While the right-hand side will depend on the functions involved in f of t and y, in the end, it will be written in terms of the Laplace transform of y. Once we do this, we will be left with an algebraic equation for the Laplace transform of y. I want to emphasize here that we'll have an algebraic equation for the Laplace transform of y. And algebraic equations are much easier to solve for the Laplace transform of y than differential equations are to solve for y, which is the case that we started in. Once we do the algebraic work to solve for the Laplace transform of y, we will be left with the Laplace transform of y as some function of s. Now, when we're trying to solve a differential equation, we're trying to find the function y that makes that differential equation true. Notice here that this does not give us y directly, but instead it gives us the Laplace transform of y. So we need to be able to find y of t by knowing its Laplace transform. This process of finding y of t from the Laplace transform of y is called the inverse Laplace transform. When solving differential equations this way, taking the inverse is typically the most difficult step in the process. So we will have to do a lot of work in getting used to taking inverse Laplace transforms. I want to note here that the inverse is well defined, meaning that if the Laplace transform of y1 equals the Laplace transform of y2, then y1 and y2 must be equal to each other. Unfortunately, the proof that this inverse is well defined relies on complex analysis, and we don't have the tools in this class to prove it ourselves. Before we end this video, I want to take a step back and look at the overarching process that we use to find the solutions to these differential equations using Laplace transforms. We start out by taking the Laplace transform of both sides of our differential equation. This will give us an algebraic equation for the Laplace transform of y. Next, we need to solve this algebraic equation for the Laplace transform of y. And once we know the Laplace transform of y, finally, we need to be able to find y by knowing its Laplace transform by taking its inverse Laplace. This is going to be the overarching method that we use in solving all differential equations using Laplace transforms.